So here we are back again at the G proof, our rigorous mathematical proof that God exists using first order predicate logic and 5 axioms no scientist can reasonably deny. This is video 8 out of our 9 videos. We're already to video 8, formal rigorous proof that God exists. This is it, where we do the actual proof. And we have a website at thegproof.org. I'm Mark Lawrence Donald Emerson. I'm your teacher, and we're ready to go with the proof. So here's a map of all our videos, and we've already done 7 of them. Look at all that cyan color. And so now we're all set up. We've covered our undefined terms, definitions, and all of our axioms, and we've shown that the axioms are consistent in videos 6 and 7. And back in videos 2 through 5, I taught you about predicate logic. We're going to use all of it now in this video. So here we are, the formal rigorous proof that God exists, and then after we're done with this video, we're going to do, in video now, we're going to talk about the consequences of the proof. Alright, so video 8 is where we are, and here's an outline of this video. First I'm going to take a minute to talk about what we're going to be using to prove the G theorem. I'm going to talk about who the authority is here, which happens to be you. Then we're going to do the proof, and then we're going to have a couple of closing remarks at the end of this video. Alright, so what are we going to use to prove the G theorem? Here we are in our outline. What we're going to do is we're going to use what we learned in videos 3, 4, and 5, which was sentential logic and predicate logic. The sentential logic is a part of the predicate logic. We're going to use that now. We're also going to use our 3 undefined terms, phenomenon, part of, and causes. And we're going to use our 3 definitions, which are C, which means causes something, and S, which means is self-caused, and O, which means is omnipotent, causes everything. And we're going to use our axioms, all 5 of them, and that's it. So now, let's talk about who the authority is here. This is where we are in our outline. Now, I am not asking you to believe that God exists. This is not religion. This is pure mathematics. What I am doing here is I am teaching you first order predicate logic. Actually, I already taught it to you. And I'm teaching you a formal mathematical theory of phenomenon and causation. We have 3 undefined terms, 3 definitions, and 5 axioms. We've been through all of that. And 3 theorems, and the monumental result that God exists. We're going to prove the 3 theorems in this video. And then in video 9, we're going to do definition 4, which is our formal definition of God. What I am doing in these videos is I am inviting you to go deep into your own intellect and comprehend all of this. So the authority here is you. My task is to help you to see and understand all of this for yourself. Okay. So now let's start. Let's dive in to the proof of theorem T1. Here we are in our outline, and theorem T1 says there exists an X such that OX. There exists a phenomenon X such that X is omnipotent. In other words, an omnipotent phenomenon exists. That's theorem 1. So here we go. Here is a statement of the theorem. Of course, we're going to use 4 columns as usual. We're going to start with a claim rule as usual. We're going to write prove that very thing up there by the claim rule. So we're proving there exists an X such that OX. Okay, there exists an omnipotent phenomenon. Okay, so now how are we going to prove this? Well, we're going to use direct proof, which means we're going to just try to get it. Okay? Once we get it, then we're done. We're going to begin now with axiom 5. This is the all causes axiom. There it is right there. And I'm going to take that axiom and I'm going to copy it into the proof. And so that is coming from axiom 5 by the rule of repetition. Remember, when we use axioms in a proof, also when we use definitions in a proof, we bring them in with the rule of repetition because they're givens. Okay? So there it is. And so now what we're going to do with this axiom, which says that it says there exists something there exists something that everything that causes anything is a part of it. Okay? That's what we called H when we went back in video 7 when we talked about this. Alright, so now look at this. We're going to look at this particular line, and we see we're going to use the rule existential instantiation because it starts with there exists an R. And what we're going to do is R is our blue variable, just like this. So we're going to put in something for R. We have to make a brand new variable because this is EI. All right? And so we're going to pick H. So we're putting H in right here where the R was. See that? We stripped off the existential quantifier and we put the H in where the R is. So that's from line 2 by EI. All right? And now we're going to use axiom A1, which is the axiom of sufficient reason. That begins with for all R. It says everything has a cause. For all R, there exists something that causes it. We're going to do what I'm going to do now in these videos, because if I put all of this into proof, the proof will overrun the screen. So I'm going to little mini parts right in here to just when we're bringing the definitions and axioms in. Watch. Okay, so I'm going to use U on this statement here. I'm going to use UI because it starts with for all R, and I'm going to put in for the R's. On the R, I'm instantiating on the R's, and I'm going to put an H in. I already have H up. I picked H because I've got it going up there. Okay, so this is what I've done is I put the H in for the R, and that is by UI from this line here. Although I'm doing sort of a mini thing in there, now what I'm going to do with that is I'm going to take it and put it in here, up here in line 4, and I'm going to say that's just by axiom 1 from UI. In other words, by repetition and UI. In other words, I repeated axiom 1 and put it in, but I'm not going to put the R. We're just going to say it's by axiom 1 UI. Okay? All right, now what? Well, now we have another existential statement here, so we can use EI again. And so we're going to, on V this time, there exists a V such that V causes H. And so what are we going to do? I can pick any letter as long as it has to be a brand new variable. I'm going to pick little g. No, excuse me, little a. I'm going to pick little a and put that there. Okay, so little a, we're going to say that causes H. And that's from 4 by EI. Okay? Now what? We're going to use definition 3. Definition 3 is for omnipotence. And here it is. For all Q, OQ, if and only if, for all T, Q causes T. Now I'm going to do a UI on this right here. So using this statement, I'm going to do UI for the Q. There's 2 Q's inside the parentheses. And what I'm going to put in there for those 2 Q's is going to be A. So I'm putting A in where the Q's are, stripped off the universal quantifier. And that is by UI from right here. Okay? And now, this is a biconditional. I have pink if and only if blue. So I can use the rule of BC going the second way to turn that into a conditional. I'm going to take the reverse conditional like this. Okay, so I've peeled off the reverse conditional going the other way. Okay, and that's from this biconditional by BC. Okay, now I'm going to take this whole thing and put that up in my proof. And I'm going to say over here, I'm going to say that's from definition 3 by, now look, I put 2 reasons here, by UI and BC. See, I'm doing that to abbreviate so that I can fit everything on the screen. Okay? Does that make sense? So in other words, if what this line says, it says for all T, if for all T, A causes T. In other words, if A causes everything, then A is omnipotent. Okay, it comes directly from the definition of omnipotence. Okay. Now we're going to make another claim. I'm going to write this. I'm going to say, let's prove for all T, A causes T. That's by the claim rule. And why am I doing that? I'm going to try to prove that because that's the left side of this conditional in line 6. Line 6 is a conditional. And you can see, if I can get the left side of it, then I can get OA, which is getting close to what I want up here, what I'm trying to prove. Okay? So I need to try to prove this now. Okay, now this here is a universal statement, so I'm going to use universal proof for that, which means, in other words, I'm trying to prove for all T, this pink statement with the T in it. That's like this right here. Well, in order to proceed on a universal proof, I have to make sure that the blue variable is not free anywhere up there. Do I have, and the blue variable is T. Do I have any T's up there? I do. I have a couple of T's right here. Are they free or are they bound? Well, it's bound. The T inside the parentheses is bound by the quantifier for all T out there. I don't see any other T's up there. That means I'm good to go on this universal proof. And so what I have to do now is I have to try to prove that the pink thing with the blue variable in it, like this right here. That's my goal right here in this nested proof we're going to be doing. Okay, so now what's next? I'm going to bring in axiom A1. which I already used axiom A1 once. I'm going to use it again. And what axiom 1 this time I'm going to use UI on this here and on the variable r. And this time for the variable r, I'm going to put in t. I can put anything I want in because it's UI. All right, so that's from right here by UI, okay? And now I'm going to take that statement there and copy it up into the proof. And I'm going to say axiom 1 by axiom 1 UI, okay? And repetition, but I'm just leave the repetition off. Okay. Well, now this is an existential statement. It says exists something V, such as V causes T. All right, well, I can use EI on that. On the V is the quantified variable here. I have to pick a brand new variable, and I'm going to pick a B. I haven't used B before. So I put B in where the V is, and I've stripped off the exists of V. Okay? And that's by 8 EI. All right. Now what? Well, now I'm going to use this rule of existential generalization. I'm going to turn right back around and put a new existential quantifier on it, except I'm going to put it on the other one. Okay, here, in line 8, the existential that exists of V, the V was on the left side of the causes. It says V causes T. Now I'm going to do it on the T, which is on the right side of the causes. Okay, the T here, see? I'm going to do that. I'm going to generalize that, and I'm going to use a variable S. So I'm going to say there exists, that's like this here. I can introduce a new variable. It has to be, I should make the point that the variable, the red variable here is indeed free, as it has to be. It's free in line 9. So now I've introduced it. I can pick any variable I want there. I'm using S. So there exists something which B causes. I know in line 9 that B causes T, therefore in line 10, by EG, I can say something causes, B causes something, okay? All right, now what? Now we're going to use definition D2. I need to put it up here just because I'm running out of space down below. D2 says what C means, the capital C. The capital letter C, that predicate means causes something. So CR means R causes something. So there's the definition. It has a universal quantifier in it. I'm going to use UI on that. And so that means for the variable R, I have to put, that's the blue variable, I have to put something in. I'm going to put B in there. Okay, so I put B in, I've stripped off the universal quantifier, so that's by U, from this by UI, okay, here. And now, this is a biconditional here, as always is in a definition, and so I'm going to now use BC and I'm going to do it again in the reverse direction, and take the biconditional, get a conditional, and that's from this one here by BC, okay? And now I'm going to take that, and I'm going to copy it into my proof here. And so this is from definition 2 up here by UI and BC. You see that? Okay. Now what? Look at these two statements, 10 and 11. I have pink here, I have pink implies blue here, so I can use modus ponens on that and get CB, right, from 10 and 11 by modus ponens, okay? Now what? Look up here in line 2. We have a universal statement in line 2, which says for all Z, I'm going to use UI on that now. So the blue variable is the Z. I've got a couple of Z's in there, and I'm going to put in for that, I'm going to put B in for the Z right here. You see, I've stripped off the for all Z, copied the pink part, and changed the blue variable to the red variable, which is now B. The Z's have changed to B's, and everything else is copied. And so that's from line 3 by UI, okay? Now what? Well, look at these. I have pink implies blue. I've got CB here. CB implies this other thing, this blue thing, so I can have the blue thing. And that's from 12 and 13 by modus ponens, okay? All right, now what? So this says that B is a part of H. All right. Now let's look at axiom A4, which is our complete causation axiom. Okay, it says that, remember axiom A4 says that if this guy causes something here which has parts, it also causes all parts. All right, and there it is right there. It has two universal quantifiers. So we're going to use, I'm going to do the universal instantiation right up here in this blue box. So we'll start with this one here, and I'm going to use UI, And so on the R, start with R because it's on the outside. R is the blue variable. There's a couple of R's there in the pink part. And I'm going to put in for that R, I'm going to put A in for that R. Okay, so I've stripped off the for all R and kept, now the pink part has the for all S in it. I haven't gotten to that yet. All right, and so that's from this part here by UI. Now I need to do, again, this time, I need to do I have another universal quantifier out here, for all S out here, and so I'm going to need to use universal instantiation again, UI again, and this time my blue variable is the S, and so I've got a couple of S's in there, and so what I'm going to put in for the S this time, I'm going to put H in. So you see I've stripped off the for all S and just kept the thing inside, the pink part inside, and put H in for the two S's, and that's from this right up here by UI, okay? And now I have that, I'm going to take the result and drop that into my proof here in line 15. And so I'm going to say the reason for that is from axiom 4, this by UI twice. I did UI 2 times, UI, UI. See that? Okay. All right, so now the next thing we're going to do is we're going to look at lines 5 and 15. Look at this, pink, and pink implies blue. Line 5 says A causes H. Line 15 says if A causes H, then this whole blue thing in here. So I can get the blue thing in there. Okay, I have pink implies blue, therefore I can get the blue. And that's from lines 5 and 15 by modus ponens. And so now, next thing we're going to do, look at this statement here. This is a universal statement for all U. So we're going to use UI. I'm putting it up here because I'm running out of room down below. And so we've got our variable of quantification is U. For all U, we've got a couple of, that's the blue variable. We've got a couple of blue variables in the pink part there. We can put in anything we want. We're going to put in B. Okay, so we're going to B's in there, stripped off the for all U, put the B's in where the U's were. And that's from line 16 by UI. Okay. Now look at lines 14 and 17. I have pink implies blue. That means I can get the blue by 14 and 17 modus ponens. Now I've got that A causes B, all right? Now what? Well, now we're going to use our transitivity axiom, axiom A2. Now it has a triple universal quantifier in front of it, 3 of them, so we're going to have to do UI 3 times. I'm going to do all that up here in this blue part. By the way, you know what I could do, if I had lots of screen space, which I don't, I could take this axiom right now and copy it right there by the rule of repetition, and then do the UIs one line at a time after that. The problem is I'm just going to run out of space. So I'm going to do it all up here and then copy the result down there to make it more compact, but you can see how it would still work anyway. All right, so here we have this statement here. We're going to use UI on that. I have for all R, doing the R first, it's on the outside, so the pink part includes the other 2 quantifiers, includes for all S and for all T. I got a couple of R's in there, a couple of blue R's, okay, and so I get to pick anything I want for the R. I'm going to pick A, so I put A in here for the R, stripped off the for all R. That's from this line here by UI. And now I'm going to do it again, this time on the for all S, once again, UI, and this time the S is the blue variable. I got a couple of S's in the pink part there, and I'm going to put in B. So I stripped off the for all S and put B's in where both of the S's were in the pink part, okay? And that's from this one by UI. And then one more time, I got for all T out here. And so I'm going to use UI again, and this time the blue variable is T. Again, I got a couple of T's in the pink part, and so I'm going to put anything I want, and I'm going to put T in. Okay, putting T, even though I can put T in, it's okay, I can put anything I want in. So I'm going to use T. I put the T's in where the T's were and stripped off the for all T in front. And that is from this line by UI. And now I can take the result and drop it into the proof right down here. And that's from, it's from axiom A2 up here by UI, 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 triple UI, okay? All right, now what? Well, look at this. In line 9 and line 8, look at line 9 and 18, I have blue and I have pink. I can put those together with adjunction. I have this and I have that, so I can say this and that. which I'm going to do right down here. I'm going to say this, I have A causes B and I have B causes T. So I'll put those together like this with adjunction. So that's by 9 and 18 by adjunction, all right? And now look, that is the left, I got pink here, and pink implies blue, and I got pink, so I can use this with modus ponens and get that A causes T. And I'm using the transitivity rule. See, I have that A causes B and B causes T, therefore A causes T. Here I've got that in fact A causes B and B causes C, therefore A causes T. So this is from lines 19 and 20 by modus ponens. And now look, we're in the middle of a universal proof up here. What we're trying to do is we're trying to prove A causes T, where T is free. And that is exactly what we have done right here. We've got the pink part in there, which means that we're done with this universal proof, okay? And that comes from line 21 by universal proof. And now I get to box and cancel, but my rule's in the way. Let me get the rule out of the way, and so I can put a box around all this and cancel the proof, okay? Now what? Well, look at this. Look at lines 6 and 7. 6 says pink implies blue, and 7 says pink. See, I've proved that that A causes everything. I've said in line 6 says if A causes everything, then A is omnipotent. So I can say now that A is omnipotent, and this is from lines 6 and 7 by modus ponens. All right, now what? Well, now we're going to use existential. We have to say exists something that is omnipotent. Well, we have A is omnipotent, so we can generalize that. We can say use existential generalization on this, where A is the red variable. It has to be free. It is free in this statement, and so then I can say that I can pick any variable I want for the quantification variable when I use e.g., and I'm going to pick x because that's what I have up here. Okay, so I can say exists in x such that x is omnipotent, and that comes from line 23 by e.g. And now look at this. That is exactly what our goal is. We're trying to prove exists in x such that ox, and so that means that we can use by direct proof. Now we have the right to say done. We're done with that. That's from line 24, where we reach the goal by direct proof. Get the rule out of the way, and so I can box and cancel the proof. And so there I'm done. Theorem 1 is now proven, okay, from our axioms and definitions by first order predicate logic. We've proven that there exists something that is omnipotent. Okay? So that's it. Theorem 1 is done. Now, so I made that one cyan. So now let's move on and do Theorem 2. Proof of Theorem 2. Okay, so here we are in our outline. And what does Theorem 2 says? Theorem 2 says there exists a y such that y is self-causing and omnipotent. Add the self-causing in now. There exists a phenomenon y such as y is self-causing and y is omnipotent. In other words, a self-causing omnipotent phenomenon exists. All right, so here it is. There exists a y such as sy and oy. And we're going to use 4 columns as usual. And we're going to start with the claim rule as usual, and we're going to do that by the claim rule. We're going to copy the very thing, put the very thing we're trying to prove right there in line 1 as usual. Now, how are we going to prove this? Well, we're going to use a direct proof as usual in these theorems. We're just going to try to get it, okay? So we're going to use Theorem 1 now. Now, since Theorem 1 has been proven, we can use it and we can bring it in. Here's Theorem 1. We have proved there exists something that's omnipotent. So I'm going to take that and copy it into the proof, and that is from Theorem 1 by repetition. Now you see, if we were doing just a big long proof, we wouldn't have to break it into these separate theorems. I broke it into theorems so I can fit everything on the screen. Otherwise, we could just, when we get done with Theorem 1, just keep going in that same proof, see? But because I'm breaking it up just to make it manageable for these videos. All right, now what? Well, look at this. It says exists something. Well, we can use EI, and so I can say I get to put something in for X. Something is omnipotent, so I get to pick something, and I'm gonna pick C, little c. All right, so I said we have something is omnipotent, and that is from line 2 by EI. All right. Now we'll use the definition of omnipotence, which says for all Q is omnipotent only if and only if for all T, Q causes T. And we get to use UI in that. And so I'm going to put, for the blue variable, which is Q, I get to pick something to put in, and I'm going to pick C. So I'm putting C in. So this comes from this line here by UI, putting C into the pink part wherever the Q's were. Okay? And now I'm going to use the rule of biconditional to conditional here, because this is a biconditional. I have pink if and only if blue. So I'm going to use the reverse one. No, I'm going to do it the forward direction. I'm going to I'm going to take the pink implies blue, take the biconditional, make it into a forward conditional, and that's from here by BC. Okay? And now I can take that result and drop it into the proof right here, and that is from definition 3 by UI and BC. Okay? Okay, and oh, you know, I forgot to mention when we did the EI in line 3 that, remember, EI always has to be to a brand new variable. I think I didn't mention that, and C is a brand new variable, so it's okay. All right, now moving along here, look what we have. We have OC, and we have OC implies C causes everything. Okay, so with pink, and pink implies blue, so we can use modus ponens, and we get that we get the blue from 3 and 4 by modus ponens. And now this says that C causes everything, doesn't it? Which means it's omnipotent. So I can use UI on that, and I'm going to put in for the for the T, I'm going to put in C. All right? And so it's by 5 by UI, okay? And now why did I do that? Well, that's because, look, see, that means it's self-causing, doesn't it? So we're going to use the definition of self-causing now, which has a universal quantifier in it. And so I'm going to use UI there on this for all R, and I'm going to put in, we have the blue variable 3 times in the pink part in here. And I'm going to put in C, of course. All right, so I got SC if and only if C causes C, and that's from right here by UI. And now I have a biconditional, and I get to turn that into a conditional. I'm going to do it the reverse way using BC. So I'm going to turn it around the other way, get the reverse conditional here from right here by BC. And now I'm going to copy that into my proof up here by definition 1, UI BC. Okay? All right. And now we have pink, and pink implies blue, so that gives us that the blue. So we get that from 6 and 7 by modus ponens, and that says that C is self-caused, doesn't it? All right, now look at this. We got C is omnipotent and C is self-caused. Let's put them together with adjunction, and we can say C is self-caused and omnipotent. Okay, and that's from 3 and 8 by adjunction. Okay, and now we can use existential generalization on this. We're just right almost to the end here. Okay, we're going to use the red variable is C. Okay, and now we're going to generalize that. We're going to say there's something, and I'm going to use Y as my variable of generalization, or the bound variable, because that's what I want up there. And so that comes from line 9 by EG, all right? And there, look, we've got it. This is exactly what we're trying to get. And so we've finished our direct proof. We can write done by line 10 where we'll reach the goal, and now I can box and cancel the proof. And so that takes care of Theorem 3. We've now proven there is something that is self-causing and omnipotent from our axioms and definitions in undefined terms. Okay? That's the proof of Theorem T2. And now it's time to move on. We're going to use that to prove Theorem T3, which is that in addition to existing, it's unique. In other words, a unique self-causing omnipotent phenomenon exists. So now we have to deal with uniqueness in Theorem 3. So here we go. Here's the theorem. Now we have an exclamation point. There exists exactly one G such that SG and OG. Okay, that's the short uniqueness formula, isn't it? There exists a unique phenomenon G such that G is self-causing and G is omnipotent. In other words, a unique self-causing omnipotent phenomenon exists. All right? So here we go. There's what we're trying to prove. We're going to use 4 columns as usual, start with a claim rule as usual, copy this down as usual. We're using the claim rule, and this is exactly what we're trying to prove, okay? All right, now, how are we going to do this? We're going to use a direct proof, and we're going to start by bringing in Theorem 2. See what this says up here? This is the short uniqueness formula. We've got to prove that, and we'll get to that at the very end after we have a lot of work to do first. All right, so let's bring in Theorem 2, which is here. We're bringing that in by repetition. Okay, that's Theorem 2. We just finished proving. which there exists something that's self-causing and omnipotent. It just exists, but it doesn't say it's unique though. All right, we have to prove there's only one of them. Okay, we're going to use EI on this. And for the blue variable, I have to pick a brand new variable, and this time I'm going to use D. Okay, so D is brand new, it hasn't been used anywhere. I put that in for the y's there, and that's from 2 by EI. Okay, and now I have a conjunction. I have the pink and the blue, so I can pick one of them off, and I'm going to pick off using simplification. Okay, if I have pink and blue, I can say blue. I'm going to pick off the blue and say OD, and that's from 3 by simplification. Okay. Now, if D is omnipotent, then, well, I need to use the definition to unlock that. So here's the definition of omnipotent, and this says, we're just going to go through the process here again and again. Remember, I'm doing this mechanically to make sure we can follow all the rules, even though it may get a little laborious, but that's how it is. Okay? And so now, we have for all Q, we're going to use UI on that, and we're going to put in, for the Q, we're going to put in D, which is what I have up there. And so that's from right here by UI, putting the D's in where the Q's were. Okay, and now we have a biconditional here. We're going to change that to a conditional the first way. We can take the forward conditional off of that. Okay, and that's from this right here by BC. Okay, and now we're going to take that and drop it into our proof up here, and that is from definition 3 by UI and BC. Okay. And now we have pink. We have pink implies blue, so we can get that D causes everything. And that's from lines 4 and 5 by modus ponens. All right. Now, for all T, D causes T. All right, we're going to make a claim now. And what we're going to claim is this. Now, why did I claim this? Okay, this is by the claim rule. Well, where did this come from? Well, look, we're trying to prove this. Up here, what we have up here is the short uniqueness formula. This is a part of the medium uniqueness formula, except that it's missing the existential quantifier in the outside. And so we're going to do this, and when we get this proof done at the bottom, we're going to use EG and put that existential quantifier on, and then we're going to use medium to short, MUMPUS, medium to uniqueness formula to short, to produce this. This is how it's going to work. Okay? All right, so now what kind of proof is this? It starts with, this is a universal quantifier, the whole thing. It's for all E, all of that stuff. All right, so we're going to use a universal proof. And so E is our variable of quantification. So we've got for all E, and then that pink statement, which has 3 E's in it. Now we have to make sure there aren't any, that E does not appear anywhere free up above. Well, you know what? I don't see any E's up here at all. So we're good to go on this universal proof. So what we have to try to prove is the pink part with the blue variable free, without the for all E in front of it. Okay, how are we going to do that? We're going to do another claim. We're going to do a third level proof now. So we have our original one, and we have nested in one, nested in again here. We're going to try to prove this by the claim rule. And why are we picking this? Well, because look at this here. In line, and by the way, let's compare these two. What's inside the parentheses here in line 7 is a biconditional. And what's on line 8 is a conditional. It's the forward direction of the biconditional up here in line 7 that's in the parentheses there. See that? Okay, I've changed the biconditional conditional in the forward direction. We're going to prove that forward direction. Then we'll prove it in the reverse direction and put them together. And that's how we're going to get line the 7 boxed and canceled. But first we're going to do this one. All right, and this is a conditional. We're trying to prove pink implies blue. Therefore, we can do a conditional proof. We can assume pink and try to get the blue. So this is from our assumption. This is our assumption for conditional proof. Now we're going to try to get the blue. All right. Now this thing is a conjunction. It's pink and blue. So I'm going to use simplification on that, and I'm going to pick off the blue here and get OE from that, and that's from 9 by simplification. And now moving right along, I'm going to use the definition again to unlock what this is. So I'm going to go through this process yet again here. Okay, so using UI on this, the variable here I have is Q, and this time I'm going to put E in for that, all right, in here. And that's from this line here by UI. And now this is a biconditional, so I'm going to turn this into a conditional in the forward direction, like this. And that here is from this line here by BC. Because if E is omnipotent, that means for all t, E causes t, right? Everything causes, the E causes everything. So I'm going to copy that in to my proof here, and that is coming from definition 3 by UI and BC. Okay, now I have pink, and I have pink implies blue, so I can use modus ponens to put them together and get for all t, E causes t. So that's from the lines 10 and 11 by modus ponens. All right, now, this here is a universal statement. I have for all t, E causes t. Well, I'm going to use UI on that, and the blue variable is t, and I'm going to put in for the t, I'm going to put D. Putting D in for the t. Now, why did I pick D? Well, we'll see in a minute. D is happening up here. Now I'm going to put a D here. Now watch, we'll see in a minute what's going to happen with this. Okay, that's from 12 by UI. Now I'm going to come up here, this one, this says that, see this one, line 12 says that E causes everything, and line 6 says that D causes everything. So if D is God, then E is God's competitor. He's trying to compete with God, because it's saying it's all, line 4 says that D is omnipotent, and line 10 says that E is omnipotent, so E's the competitor. So what we're going to show is we're going to show that D actually equals E, so there's no real competition, all right? All right, so up here on line 6, we're going to use UI there, and our blue variable is t, and so we get to pick anything we want to put in, and so we're going to pick E. All right, so look what I did. I put E in there. I took off the universal quantifier. I took off the for all t, and I put E in where t is. Okay. All right, and now that's by 6 by UI. All right. Now look. We have right here. We have pink and blue. We're going to put these two together. We have E causes D, and D causes E. Now think back, there's one of our axioms that is that matters here. Okay, we're going to use adjunction to put these two together, and so we have from 13 and 14 we have E causes D and D causes E. We put them together. Okay, and now what we're going to do is we're going to use axiom 3, our non-circularity axiom. See, this non-circularity axiom says well, using R and S, it says if R causes S and S causes R, then R and S are equal to each other. See, that's what's going to happen here. But we're going to go turn the crank and go through the whole process. I promised you. Okay. All right. So now we're going to use, this is a universal statement here. It's got a double universal quantifier on it. So we're going to use UI on that, and we're going to put in our variable for that. First, we're going to do the R on the outside. So we've got some R's. We've got 3 R's in the pink part inside there, and for those, we're going to put in E. Okay, so I put E's in for the R's and stripped off the for all R. So that's from this here by UI, okay? And now we're going to do it again. We have S for all S out here. So we're going to use UI again on that. And we have the blue variable is now S. And so what I'm going to put in for that, I'm going to put D in for that. And so the S's have become D's now, stripped off the for all S. And so that's from this one here, again by UI. Okay, did a double UI, double U, I don't mean the letter W, okay. And so now this line here, I'm going to take that and drop that into the proof here. And that is from axiom 3 by UI twice, UI, okay. All right, and now, look at this. So we have pink here, and we have pink implies blue here, therefore we have the blue. We just proved that E is equal to D. See that? And that's from lines 15 and 16 by modus ponens. All right? And now, look, this is our goal. We were trying to prove pink implies blue here in line 8. We assumed the pink, and we just got the blue, right? That's a conditional proof, isn't it? That means we're done. And we're done because we reached the goal in line 17, so that's by conditional proof. So that means we get to box and cancel the proof on our nested proof here. So now we've proven in the forward direction this pink implies blue. Okay, so we've proven a piece of this thing in the forward direction. Now we're going to do it in the reverse direction by using the claim rule again and writing this. So this is by the claim rule, and you can see now we're doing the same thing in the reverse direction. So lines 8 and lines 19 are the reverse of each other. Okay. All right. And so this is another conditional. We're trying to prove pink implies blue, so we get to assume the pink and try to get the blue. And this is it's a pink. This is our assumption for conditional proof. We have to try to get the blue now. Well, guess what? This is going to be easy. We have our rule substitution of equals, and look up here in line 3 and down here in line 20. We have that D is both self-causing omnipotent and omnipotent. That's like this in the substitution rule. And we have that E is equal to D. That's like this. That means we can plug the E in where the D is up here, right? So that's what we're going to do. We're plugging the E in for the D here. And that's from lines 3 and 20 by substitution of equals, okay? Well, that's our goal. We just did it real fast, okay? So we got this one done quickly, and so we tried to prove pink implies blue. We assumed pink. We got the blue in the very next line after that. And so this is done from line 21 where we reached the goal by conditional proof. So we get to box and cancel this proof here, this proof. All right, now look. We've proven the forward conditional here and the reverse conditional here. Pink implies blue, blue implies pink. And that means we can use CB to put those together to say pink if and only if blue, right? And so that's what we'll do down here, okay? So we've got pink if and only if blue down here, and that is coming from lines 8 and 19 by CB, because 8 and 19 are, the proof is canceled out on both of them, okay? All right, now look. We're in the middle of a universal proof here in line 7, where we're trying to prove this pink part in here without the for all E on the outside, where we have the E's free, the blue variable is E. And look what we have down here. We have down here exactly what it says in the pink part up here with the blue, and the E, which is the blue variable, is free in line 23. So that means that we're done. We're done with that universal proof. And that's from line 23 where we got the pink part in here without the universal quantifier in front of it, and that's by universal proof. I'll get the rule out of the way, so now we get to box and cancel this proof, okay? All right, now what? Well, we're going to use EG, and we're going to use it on this here, okay? Because this is almost the medium uniqueness formula, but not quite. We're going to use it on D. We're going to take that D, and we're going to make that, we're going to say exists something. And we're going to do that right here. I'm going to use the letter F. Exists an F, I'm sorry, we're going through the alphabet with my new variables. Exists an F such that all of that pink stuff, I've copied the pink stuff from here into there, and I've changed the red variable D into the blue variable F down here. So that is from line 7 by EG, right? Now look at this. Here in line 25, we actually have the medium uniqueness formula. You might not quite recognize it. It's a little complicated. So what I'm going to do is I'm going to put up here on the screen our Muffus rule from video 5, which shows the form of the medium uniqueness formula. And I'll compare this with line 25 very carefully in a moment. Now if you remember, in video 5, we had 3 uniqueness formulas. The long one, LUF, long uniqueness formula, the medium one, MUF, and the short one, SUF. And the long one was very clear that it meant at least one and at most one. We could look at the predicate logic and clearly see that, yeah, it actually says that. The medium uniqueness formula is shorter and easier to use, but it wasn't obvious. We couldn't look at it and just see, oh yeah, of course, that means exactly one. It wasn't so obvious, which we spent a lot of time in video 5 proving that the LUF and the MUF were equivalent. We proved the LUF implies the MUF and that the MUF implies the LUF. So because we did that proof, we know that the medium formula, the MUF, does mean uniqueness. And here it is right here. And what it says is whatever this pink statement is, this pink thing is a statement that is either true or false depending on what the red variable is. The value of the red variable is either going to make that pink statement true or false. And what this says is that exactly one thing makes that pink statement true. Okay? And then the short uniqueness formula is very compact, and it has our new quantifier, or the uniqueness quantifier, the backwards E with the exclamation point. And it simply says exactly one thing makes that pink statement true. Okay? All right, now let's make sure that what we have down here is the uniqueness, the medium uniqueness formula. So I'll put the color on here. So we make this yellow like this. Now we want to see that this is exactly in this form. So let's check it. First of all, what I've done down here is I've made the variable f blue and the variable e red. Okay? So let's start at the outside. This says there exists a blue variable. And down here we have there exists f, which is the blue one. And then just inside that we have for all of the red variable. And right here we have for all e, that's the red variable. And then we have these parentheses with this big thing inside. Okay? And what is that statement in the parentheses? It is a biconditional. Right there, there's a biconditional. And we have down here, right in the middle, there's the biconditional. Okay? So this is matching up. So now let's look on the left and the right of the biconditional. On the left of the biconditional here we have the pink statement with the red variable in it. And down here we have, to the left of the biconditional, we have a pink statement with the red variable in it. And specifically we have SE and OE. In other words, E is self-caused and E is omnipotent. Okay, that's our pink statement. And so well, let's finish this first. On the right-hand side of the biconditional, we have an equation that says the red variable equals the blue variable. And that's what we have down here. We have on the right of the biconditional, E equals F. The red variable equals the blue variable. So this down here is exactly in this form. So what this formula says is exactly one thing makes the pink statement true. What this down here says is that exactly one phenomenon is self-caused and omnipotent. Exactly one phenomenon makes SE and OE true. All right. So now, since we have this form, we can use our Synopsis rule to get the short uniqueness formula, which is what we want for what we're proving. So let's do that now. Okay, so now we're going to introduce the purple variable, which is going to be G. So what happens when we go from here to here is we rewrite the pink statement and change the red variable to a purple one. And then we get rid of all the rest of that junk, and instead on the outside we put the quantifier, the backwards E with the exclamation point, and the purple variable to say there's exactly one purple variable that makes that pink statement true. And look what we have here. We have changed in the pink statement in line 25 where we had the red variable. We've changed that. We've copied that pink statement down here, but changed the red variable to purple. We've changed the E to G. All right? The other thing that we did, like here, is we now have on the outside there, we have backwards E with the exclamation point. Is this exactly one? And then the purple variable G. So this right here says there exists exactly one G, such as SG and OG. Now, where did that come from? That came from line 25 by Synopsis. And so now what? Look, that's it. We have gotten what we're trying to prove here. We've proved that there is exactly one G, such as SG and OG. And this is from, that's our goal. And so that means we're done. We've got the thing we're trying to prove. So this is from line 26 by direct proof. And so now we get to box and cancel. And there it is. There's theorem 3. This says there exists exactly one thing which is self-causing and omnipotent. And that's our theorem 3. This is our result in these videos. So we've done it. We've got the proof that theorem 3 is done. In other words, God exists. A unique, self-causing, omnipotent God exists. All right, now I have a couple more things to say at the end here before we finish the video off. Okay, we have proven that God exists. Here we are in our this last little closing points that I want to make here. And so we have learned about first-order predicate logic. Our axioms Our 5 axioms are simple, sensible, reasonable, and they reflect observable reality. We've shown that our 5 axioms are consistent with one another. And using the 5 axioms and first-order predicate logic, we have proven Theorem T3, which says there exists a unique G such that SG and OG. In other words, there exists a unique phenomenon that is self-caused and omnipotent, which means we have proven that God exists. And the proof is rigorous. We followed the rules of first-order predicate logic mechanically. I know it got a little drawn out, a little laborious, a little tedious, but that's what we need to do to be rigorous. There's no room for debating or disputing whether the proof is correct. The proof is definitely correct. Now, there may be some room for discussion about the axioms and how all of this relates to science, and we're going to talk about that in video 9. So, from the point of view of pure mathematics, what we have done here is we've created a window out of pure mathematics. And if you understand all of this, if you understand the predicate logic and the axioms and the proof, and you can look at all of that and look at the proof and go, yeah, I get it. Well, by doing that, you're looking right through this window at God. You can see God by understanding the mathematics in your own mind. If you can take this all into your own consciousness and own it, then it's yours. And you can see God with it. And I hope I have been able to give that to you. That has been my intention, to show you that God exists. Okay, so we're at the end of video 8 now. What we are going to do is take Theorem T3 and use it in video 9 to make a formal definition of God, you see with the candy cane. Anyway, so that's it though for video 8. It's also it for videos 6, 7, and 8 when I have presented the proof. And we're going to use all of this stuff, the whole concept of the proof and the axioms and their consistency in video 9 as we talk about the consequences. What does this mean for science? What does it mean for atheism? What does it mean? What's the impact on religion and psychology, education, law, and government? We'll do all of that there in video 9. And so here we are. We've got 8 of the videos cyan colored now, almost done. 1 more to go. Video 9. I hope to see you there. Thank you so much for watching. I'm Mark Lawrence Donald Emerson.